The code.
I'm attending this seminar, so yeah, it's okay. Can I get some more coffee?
So we'll wait 1 minute after the hour and then we'll start.
Okay. So during my talk, I should stop my video or?
No, it's fine to have your video.
It's fine. Okay.
Others are welcome to have it. Actually, I think it's generally nice to be able to see the speaker. So.
Okay. We'll keep this San Francisco.
Yeah, right. But whatever you prefer, if you want to.
Okay. Oh, it's moving. I don't know why.
Okay, well, I think we'll get started. So welcome to the One World Probability Seminar. There'll be 2 talks today as usual. First talk is by Makiko Sasada. Before we start, let me just explain. So during the talk, if you have questions, which I hope you will, you can put them in the group chat and others will try to respond, including the second speaker. If there are questions that really are necessary that we raise them to the speaker, then the chairs will do so during the course of the talk. Otherwise, there'll be a chance to ask questions at the end as well. And at the end of the talk, we'll allow everyone to unmute themselves and join together in applause for the speaker. So it's a pleasure to have, as our first speaker, Makiko Sasada from University of Tokyo, though her picture looks like she's in San Francisco, though I think she's actually in New York, who will be speaking to us about hydrodynamic limits of non-gradient models. So Makiko, why don't you take it away?
Okay, thank you very much for introduction. It's a great honor to give a talk in this One World Probability Seminar. So today I will talk about hydrodynamic limit of non-gradient models as an introduction for the second talk by Kenichi on our recent work on an abstract and geometric approach to hydrodynamic limit theory. Sorry, it doesn't move. Okay, so my talk, this is first talk, is about what is hydrodynamic limit and especially what are gradient and non-gradient models. And then I'd like to focus on one important theorem, which is used in the non-gradient techniques, non-gradient method called decomposition of closed forms. I will explain this theorem. And then Kenichi will talk about our result, starting from abstract settings, and then geometric version of decomposition of closed forms, and then he will explain how algebraic and geometric theory and techniques appear in the problem from statistical mechanics and probability theory, because he is not probabilist actually. So, okay. So what is hydrodynamic limit? This is a method, one of method to give a rigorous mathematical foundation for non-equilibrium statistical mechanics. And especially it's a kind of derivation of deterministic macroscopic partial differential equation from stochastic microscopic dynamics, more precisely stochastic microscopic interacting particle system. And law of large numbers works through some space-time scaling limit, and also we take a number of particles goes to infinity by this scaling, and we derive macroscopic PDE. And the name hydrodynamic limit comes from the idea of the hydrodynamics, deriving hydrodynamic equations such as Euler equation or Navier-Stokes equation. And the key notion is local equilibrium. So we formulate and prove local equilibrium and then derive this PDE. This is an idea. And so I will explain a bit more about the heart of hydrodynamic limit, which is very heuristic idea. So now the starting point is a microscopic system should have a large degrees of freedom, and there should be some complicated interaction between particles. So in other words, there is a strong mixing between particles dynamics. And so we expect that equilibrium states are characterized by a few macroscopic parameters. More precisely, in mathematical words, we should be able to characterize all invariant measures by a few macroscopic parameters. For example, this is one equilibrium state parameterized by macroscopic parameter rho star. Rho may be density or temperature or anything as you like, and this one is another equilibrium characterized by rho star star, or parameterized by rho star star. And then even if the system is not arrived to global equilibrium, we expect that around each macroscopic space-time point, for example, like this point, locally, the microscopic state should be very close to an equilibrium state with the parameter which depends on the space and time. So around this point, microscopic state is very close to state like at this point. So, and this point, around this point locally, the equilibrium microscopic state should very close to the microscopic state around here. And but the parameter should depend on the macroscopic point and time. So this kind of situation is called local equilibrium, and we somehow formulate mathematically what is local equilibrium, and we prove this holds. And this is theorem is called local ergodic theorem. And then the parameter depending on the point macroscopic space point and also time. So now, so if we start from this as initial local equilibrium, then maybe at some time t, we should have another local equilibrium, which is characterized by rho tu, but this rho tu should evolve smoothly in time and space, and then we should be able to get partial differential equation for this macroscopic parameter. So this is the idea. Okay. And typical microscopic models and their state space are as follows. And so there are many models where we can study a hydrodynamic limit problem, and actually already studied. And first simple example is the lattice gas. A very important example is lattice gas. So it is in interacting random walks on a lattice space. For example, exclusion process or multi-species exclusion process. So there are couple type different species of particles or generalized exclusion process. So this case, all particles are indistinguishable, but at each site, there are at most couple particles can exist. And also the range process, which include also independent random walks. And also there are other models called Ginsburg-Landau dynamics, which is Brownian interface model in a lattice. And also system of oscillators plus stochastic noise is also in this category, or energy diffusion or energy exchange model, which is obtained as a mesoscopic stochastic model from some microscopic deterministic model. And in this case, the state space is given by R plus to ZD. So anyway, all models have state space, which is given by kind of product space. And ZD is a underlying microscopic space, discrete space. And ZD may change to discrete torus or some other discrete lattice subset of ZD, depending on the macroscopic space we want to consider. So this macroscopic space is the space for PDE. Okay, and of course, discrete torus appears when we consider continuous torus as a macroscopic space. And motivation of our work is our work with Kenichi and Yukio Kametani. Sorry, is so far all previous works consider specific models. So of course there's a model independent strategy of proof, but there's no abstract theory for hydrodynamic limit, and we often use some specific property of the model we consider, and even we do not notice that so which specific property we use. So because of that, there are many interesting models for which hydrodynamic limit is expected to hold but not yet proved, because when we try to apply an existing strategy to a new model, we quite often find a new trouble or new difficulty of this model, and we notice that we had a nice property in that model, the one studied before. So our long-term goal is to construct an abstract theory of hydrodynamic limit and make clear which property is relevant or what kind of property is most important and so on. But of course, we want to start from some concrete model. So I want to explain about exclusion process. So let's start from very simple model, which is exclusion process on the torus, one-dimensional torus. And then the underlying space is a discrete torus, one-dimensional torus, and this is a state space. And an element of state space is denoted by S and called configuration. And Sx equal 1 means there's a particle at X, and Sx equal 0 means there is no particle at X. And so this is a typical configuration. And so there's an exclusive interaction between particles because there's at most one particle at each X. So the process is called exclusion process. And dynamics of symmetric simple exclusion process is as follows. So each particle has its own bell, which rings at a random time with exponential distribution with expectation 1 independently. So this one is constant and it does not depend on the configuration, local configuration. So it's called simple. And when one of bells rings, the particle chooses a target site from nearest neighbor sites with probability 1/2. And because this is symmetric, so it's called symmetric. And if the target site is empty, the particle jumps to the side. And if the target site is occupied, then nothing happens. And reset all bells or equivalent with the bell of the chosen particle and repeat the same procedure. So this is a dynamics of SEP or symmetric simple exclusion process. And so this particle moves to here with rate 1/2, and this also is rate 1/2, and this evolution is reversible. And more precisely, this is a continuous time Markov process. on this state space with generator L, and L is given by this formula explicitly. And this SXY is a configuration obtained from S by exchanging the occupation variable at X and Y. So it's just saying SX, if SX equals 1 and this Y equals 0, then this 1 goes to Y with rate 1/2. And more generally, exclusion process on ZD is given by this generator L, but with jump rate Rxy. So this is again continuous time Markov process. And so this jump rate Rxy should satisfy the followings. So first, translation invariant. And then second, okay, so tau is a shift operator, space shift operator of configuration. And it is local, so interaction is local, means Rxy is a local functions, namely it depends only on ST for some finite, through some finite set. And X and Y are not in lambda a priori because we already have this indicator function here. So means so this total rate is non-zero only when Sx equals 1 and Sy equals 0. So we can assume that our Xy does not depend on Sx and Sy. And also it's finite range. So means the length of jump is bounded. So only X and Y, the distance of X and Y are less than or equal to R, the jump may occur, but otherwise it's 0. And also non-degenerate. So it means somehow from any point, any position X and Y in CD, sorry. So between X and Y, there's some path from X to Y such that this jump rate is positive for all S. And it means so any particle can go to any place, any point at some finite steps. And typically, I mean, more precisely, okay, sorry. So any configuration can go to different configuration, at least the number of particles are same. And typically we assume that at least this nearest neighbor jumps are positive. Okay. And especially if Rxy is just constant, then we call simple, and Rxy is Ryx for all S, then we call symmetric. Okay, and the first step of hydrodynamic limit was the characterization of invariant measures, as I explained heuristically. So go back to simple symmetric exclusion process case. So the number of particles on this discrete torus is a unique conserved quantity. So there should be one family of invariant measures parameterized by this number of particles, total number of particles K. And especially by the dynamics, we can easily check that the uniform probability measure on this state space with fixed number of particles is a invariant measure and also reversible measure for this case. And the principle of equal a priori probability is a consequence from the definition of model. And this is different from the equilibrium statistical mechanics, which starts from this measure, kind of probability measure. And moreover, this nu and k converges to nu rho in distribution as n goes to infinity, and also we put k over n goes to rho, and nu rho is a Bernoulli product measure. So the density characterizes invariant measure. So this means our macroscopic parameter is just the density of particles, and we hope to derive the evolution equation for the density of particles as n goes to infinity. And from here, so there should be some explanation about local equilibrium or local ergodic theorem, but because so I want to go more details about non-gradient systems, so I will not talk about this point, but I will just give a statement of the hydrodynamic limit. And for this, introduce empirical measure. So pi nt is a diffusively scaled empirical measure of the density of particles or number of particles. And so pi nt is defined in this way. So this is a measure on torus, random measure on torus, and here we put a Dirac measure or delta measure at point x over n if x is there is a particle at x, and also so this is space scaling is 1 over n, and we also scale the mass of particles because otherwise the number of particles goes to infinity and total mass also goes to infinity. So we make also scaling of mass of particles, and also we introduce time scaling, which is diffusive because dynamics is symmetric and there's no net drift. And so this is a random measure. So pi nt is a empty valued random variable, and mtn is also the stochastic process. And typical statement of hydrodynamic limit is as follows. So suppose pi n0 converges to a deterministic measure, rho 0u du in probability. So rho 0u is a macroscopic density profile, which is a function on torus, a continuous torus, and taking value between 0 and 1. And which the point, and the important point is this is deterministic. And then for any time t, this random measure pi nt also converts to some deterministic measure rho tu du, and moreover, this rho tu is a unique solution of the following heat equation. So in this way, we obtain PDE for the density of particles. And from here, somehow surprisingly, we find that the exclusive interaction does not change the macroscopic evolution compared to independent particles, because independent random walks with same jump rate should also give the same equation. And of course, if we add more interaction between particles, then exclusive interaction plays some role, but the exclusive interaction only does not change the equation. And also reversible macroscopic evolution is derived from reversible microscopic dynamics rigorously. And what happens for other exclusion processes? And first, let's check invariant measures. And jump rate is non-degenerate, so always there as a number of particles is a unique conserved quantity, and there should be one family of invariant measures which is parameterized by the number of particles, k. And especially nu nk is a uniform measure if the jump rate is simple or symmetric. And so nu rho is product Bernoulli measure. And the nu nk is also more reversible if the jump rate is symmetric. And so we introduce again this scaled empirical measure pi nt, but here the time scaling depends on the jump rate of the process. And the hydrodynamic limit equation becomes as follows. For asymmetric nearest neighbor exclusion process case, namely the jump rate from x to x plus 1 equal p, and x plus 1 to x is q, and p and q are different case, then we take Euler scaling because there is net drift. And the limiting equation is this Invariant-Burger's equation. So I will explain later why. And next, consider symmetric and not necessarily nearest neighbor simple exclusion process case. Then, since this is symmetric, we take diffusive scaling, and the limiting equation becomes a diffusion equation. And diffusion matrix is constant, which is given by this way. So here, jump rate appears here. So it's a linear equation, and it's same for independent random walk case with the same jump rate. And the last case is the most difficult but interesting case. So if we consider symmetric exclusion process, but not a simple case, then since the dynamics is symmetric, we take diffusive scaling again. But now the diffusion matrix depends on rho, so it's not constant anymore. And this is given by variational formula, which is equivalent to Green-Coulomb formula and not explicit anymore. So we only know the variational formula for this. Okay, so the summary of the formalization of hydrodynamic limit is given here. The general assumption on the microscopic system is, so we assume translation invariance and time shift invariance, and also dynamics is local, and these are very important. And there are some conserved quantities, which is related to macroscopic parameter, like number of particles or total energy or total momentum. And also, so there's some good mixing on the state space with fixed conserved quantities. And then macroscopic parameters are given by rho 1 to rho c. So c is the number of conserved quantities. And so each associated to the conserved quantities, such as density, temperature, velocity, which characterize invariant measures. And the hydrodynamic limit is a convergence of properly scaled random empirical measures associated to conserved quantities to a deterministic measure on the macroscopic space at each macroscopic time t. So the point is each empirical measure is associated to a conserved quantity. So, and the hydrodynamic limit equation is a PDE for the density of the limiting deterministic measure with respect to the Lebesgue measure. This is a very general formalization. Okay, so now I want to go into details how to derive how to guess the equation, limiting equation. So, okay. So now we start from simple symmetric exclusion process again with generator and square Ln instead of Ln, because now we consider time scaling n squared. So then the h, let h be a smooth function, smooth test function. And then, so when n is enough large, we expect that this integral with respect to this random measure, random empirical measure is quite close to this macroscopic integral with respect to this macroscopic profile rho du. And this is by definition equal to this. And so by taking a time derivative of both sides, then we expect this is close to this. And by definition of generator, of property of the generator, this is exactly equal to this term. But here, so Sx is of course considered as a function on the configuration space. So S to Sx, and we act this generator to this function, then we can calculate it explicitly. So and by very simple computation, we get this generator, this function acted by a generator is written in this way. And especially letting W to be the current from x to x plus 1, so the current of particle, then this term is given by the current from x minus 1 to x minus current from x to x plus 1. So this is a net change of occupation variable Sx. Okay, so, and so this term is calculated explicitly in this way. And since this term is a gradient, space gradient, or the difference of one function and its spatial shift, so we can do integration by parts, and we put this spatial gradient to the test function. And then we get this term, and one n is absorbed in this discrete gradient. for test function. And again, since W is again the gradient or a space gradient or the difference of one function and its shift, so we can do the integration by parts again, and we can put this gradient again to the test function, and then we get a discrete Laplacian of H, and this N is absorbed again into this discrete Laplacian. And so again by local ergodic theorem, or yeah, so since this is an integral with respect to empirical measure of Laplacian H, so we expect this they are close, and so we can close the equation as the time derivative of this is close to 1/2 of rho tu of Laplacian H, and again by integration by parts, this Laplacian comes to rho this side. So we have a heat equation. And the point is we can apply the summation by parts twice because the current is a space gradient. And the diverging term n squared is absorbed in the discrete derivative of, more precisely, Laplacian of H. And next, we consider the implicit Burger's equation from ASEP. In this case, again, we can write this term is the current from x minus 1 to x minus current from x to x plus 1. This is always the case. But now current is not a space gradient, but anyway, we only accelerate the dynamics as n, not n squared, because it's asymmetric. So just by one integration by parts, we have order 1 term. So this is order 1 term. And now we use a local ergodic theorem to replace this term, this current, to some function of density of particles. So more precisely, we expect this local function is close to expectation of this function under some invariant measure, but this invariant measure, the parameter of this invariant measure is depends on the macroscopic parameter rho t and x over n. So macroscopic space-time and space-time point. And then this expectation is explicitly calculated as p minus q times rho times 1 minus rho, because nu rho is just Bernoulli product measure, and we know what is current explicitly. So by replacing this term to this term, p minus q rho tu, 1 minus rho tu, which depends on t and u, we get, and replace this discrete derivative to a continuous derivative, we get this closed equation. And again, we do the integration by parts again to put this derivative to this side, and we get implicit Burger's equation. So as you can see, Euler scaling and the diffusive scaling is determined by the expectation of current. So more precisely, so we can always write this Sx acted Lsx as a sum of current from x minus z to x minus current x to x plus z for all z, and here z is taken over half of zd somehow. So zd is divided into disjoint subsets, and we can always apply the integration by parts once because of this form. This is always a space gradient, and then let Wi be the microscopic current of i's direction. Then gamma I rho, which is the expectation of Wi rho, Wi and the invariant measure, is non-zero. Then the hydrodynamic limit scaling is Euler scaling, and we expect this hydrodynamic equation like ASEP case. And if the expectation of current is 0 for all invariant measure, so then the hydrodynamic limit scaling should be diffusive, because Euler scaling under Euler scaling time, we don't see any movement of the particles at macroscopic level. So, and then diffusive models are categorized into gradient and non-gradient models. So actually, gradient models are some nice models, and non-gradient models are just models which not gradient models. Anyway, so let EJ be a normal basis of ZD. Then the gradient condition is given as follows. So if there exist local functions Hij such that this Wi, the current for ith direction, is given by the sum of space gradient of this Hij in the direction j, then for all I, so then the model is said to satisfy the gradient condition, or the model is of gradient type. So and this simple symmetric exclusion process on Z, it satisfies the gradient condition on Z, or on torus also satisfy the gradient condition, because W1, it's because this is one dimensional, so there's only one direction, but W1 equals W101 is given by the shift difference of H and its shift. So, and H is just this function. And if the model satisfies this gradient condition, then the second integration by parts is possible. And the hydrodynamic equation is given by this one. So Hij tilde is the expectation of Hij under invariant measure. And the Dij is also given explicitly in this way, using Hij and Hji. So it's quite explicit, and we only need to prove a local ergodic theorem for this case again. And the most difficult case, but more general case, is a non-gradient case. So if it's not a gradient type, the model is not gradient type, then we have to do a very tough argument and to control the formally diverging term. So it's order n term. So let Ui be this space shift space gradient function, SEI minus S0. Then heuristically, what we show is that this current in ith direction is approximated by sum of Dij times Uj plus some function which is in the range of generator L. So L is a generator for infinite dynamics generator, and F is some local function, and Dij is a constant, and Uj is these functions. So we want to replace this current by some gradient function, space gradient function. So it's called gradient replacement. And of course, this should have some precise meaning, and as n goes to infinity and in some space. Anyway, then if we can prove this, or we can justify this, then we can apply the integration by parts for the first term, this term, because this is a gradient. And we can also show that second term, this term is converts to 0 as n goes to infinity. So this term is highly oscillating term. So this is goes to 0. This part is not hydrodynamic limit for general case, not only non-gradient case. So entropy method, there are mainly two famous methods of proof, strategy of proof. The one is entropy method, and the other is relative entropy method. And both are introduced first for gradient and reversible models, and then generalized to non-gradient case, and non-gradient reversible case, and non-gradient non-reversible case later. And entropy method use the entropy of the dynamics with respect to some invariant measure. But relative entropy method use entropy of dynamics with respect to some homogeneous invariant measure or local equilibrium, more precisely local equilibrium. So it's a bit different, but also this entropy method requires the uniqueness of the weak solution of PDE, but relative entropy method requires the existence of the smooth solution of PDE. So there are some technical difference, but anyway, the decomposition of closed forms is essential for non-gradient models in both methods. So we cannot avoid this decomposition, which I will explain later. And this strategy of its proof means decomposition proof established by Baradan requires very tough argument, which is not just a routine for each specific model. So this part is open for many models, many non-gradient models. And so what happens for non-gradient models? Now consider symmetric exclusion process again, typical features of non-gradient. But this is symmetric, so invariant measures are Bernoulli and especially reversible. And we also assume that the jump occurs only between nearest neighbor sites. Then a generator is rewritten in this way. And especially if we introduce nabla and nabla tilde, the operators in this way, then the Dirichlet form of this with respect to this generator is given by this way, this one. And so here nabla tilde, but this is more precisely explicitly given by jump rate times this simple operator. And so we denote by this dxx plus ei rho as a Dirichlet form for this bond xx plus ei. Then the diffusion matrix is given by this way. So the limiting macroscopic diffusion matrix is symmetric, and also its quadratic form is given by this variational formula. And the point is, so here we have a Dirichlet form of the dynamics, and this part is quite universal for many different models, between different models. So not only for exclusion process, but many other models like continuous models or generalized exclusion and so on. So we always have this form, this universal form. And the infimum is taken over all local function. And I wrote here Xi, but Xi is just Xx is just Sx, but I want to emphasize that this is a function. So not just so occupation variable at Sx, but this is a function. And then this is a conserved quantity. And okay, chi rho is static compressibility. So this form is quite universal, and it's also equivalent to Green-Coe formula. But this part, there are two infinite sum, and both are not well defined precisely, but their derivatives are well defined. Means once we act operator nabla, this nabla, then it's well defined, and so Dirichlet form is also well defined. But this is one difficulty of this theory. And the gradient replacement and the decomposition of Hilbert space is related in this way. So now we consider A0 is a space of functions, local functions, which have average 0 for all invariant measures. And then Wi, the current, is all in this space because by assumption. So because we consider diffusive scaling model, or also we can check easily by symmetry of the dynamics. And also Ui are in this space because nu rho are translation invariant. And also L of function, any local function, LF, are also in this class because new row are invariant measures. And so H row is, so we consider H row a Hilbert space equipped with a pre-inner product on this space A0. And I don't explain what is this inner product, but so we consider some Hilbert space, which is a completion of this A0. And applying the decomposition of closed forms, we can prove that this Hilbert space is decomposed into the space of the range of local function and its completion, plus just a finite dimensional space, which is spanned by Wi. And also, this is equal to this space plus this finite dimensional space, which is generated by Ui. So then this means Wi, there is some Dij, but Dij depends on rho because the Hilbert space itself depends on rho. But that Wi plus this J equal 1 to D, Dij rho J is in this space. So means this is just the translation matrix of basis from Wi to Ui. And gradient condition means is equivalent to just space generated by Wi is equal to space generated by Ui. So once the decomposition of closed form is proved, then we can see that we can show that the gradient replacement holds. And how to okay, so how to formalize this decomposition of closed forms. So now we want to consider Hilbert space of shift invariant one forms, so instead of functions. And this is analogy to the differential forms on Riemannian manifolds. And first we consider function f to this nabla x plus EIF, the set of functions. This operation is kind of differential, like analogy to f to df for manifolds. And then we consider the set of local functions indexed by x and I in this way is one form. So we consider this W is a one form, and so this space is a set of one forms, and W is set shift invariant if Wx x plus EI is given by the shift of W0 EI for all x and of course for all I. And then we consider set of shift invariant local one forms, but this is just a set of local function, D tuple of local functions. So the function W is the tuple of local functions indexed by I. So this is just very simple space, but we consider this as a shift invariant local one forms by extending it as this way. And then we introduce this round operator round map from local function to this space, the tuple space local function by this way. And now we introduce inner product in this one form space, space of one forms. This is also an analogy to a Riemannian manifold because Riemannian metric is actually inner product of the space of one forms or tangent space. So the inner product is defined by this way. So here we use the invariant measure new row and also, invariant measure and jump rate R. But before that, we did not use any information about new row or jump rate. So the nabla is defined independently from a jump rate. And also these spaces are independent from the jump rate or invariant measure. And then, of course, it's easy to check that this is the inner product give this relation or Dirichlet form. And we define K row is a completion of this space, the tuple of space with respect to this inner product. And then the decomposition theorem of closed forms is stated as follows. So first, let me emphasize that to state this theorem, we need the data. First, configuration space. What is a configuration space? And what is a differential operator? And we need a Hilbert space or the inner product of this space. And once we know this data, we can state what is the decomposition theorem. And especially for exclusion process case, suppose W is in this Hilbert space, so it means a shift invariant and closed form. So I don't explain what is closed form in this talk, but Kenichi will explain the next talk. So just I think this is kind of a condition like a closed form on manifold. So similar type of condition. And then W is given by a limit of this specific form, the sum of specific form. And this part is given by space shift of local functions or local function. And so it's shift invariant somehow. And this part is exactly appeared in the diffusion matrix. So here C is given by conserved quantity and Xi is just this one. And so it's not shift invariant. And again, they are not well defined, but after applying this round operator, then they are well defined function. And so this W is always given by this way. So this is a decomposition of closed form. And once we have this, so why we can show this decomposition of H-1 space, because so the space of closed form, and we define this space of exact form by this way, and we also introduce these specific forms, which we can think as harmonic form. Then the decomposition theorem says that this space closed forms decomposed into exact forms plus some finite dimensional space with this specific form. And actually there are isomorphism between H row, this Hilbert space for H-1 norm, and closed forms of one form isomorphism with this relation, and especially LF in this class is mapped to this function, and WI, the current, is mapped to this specific function, specific form. So from this decomposition, we can easily show that this is also decomposed in the space of range of generator plus current. And also, on the other hand, this decomposition is just orthogonal decomposition with respect to the measure. So we have other decomposition, and by checking the dimension of this codimension of this space. And actually, this structure is very common for non-reversible models. So configuration space is always given by S to ZD, so some product space, and S is just one side or one particle state space, and L is a generator, and the Dirichlet form is always given by this form, often given by this form, and R is some local function, which is positive, and the nabla is very simple operator, and especially homogeneous for ordered pairs XY, and this acts only on SX and SY. So somehow interaction is only in this local function, which gives speed of interaction, the speed of dynamics. And for example, multi-species or multicolor exclusion process is given by S of this space. One side space is this, and the nabla is again just exchange the occupation variable. And of course, here we can put any interaction between particles, and of course the jump rate can depend on the species, also some different interaction between different species, but they all put in here. And generalized exclusion process is also in this form, and Ginsburg-Landau process is also in this form, which Navla is now differential and not this discrete derivative, and there are several models of this type. And the one interesting model is actually there's a type like Navla is given by this integral operator. And this arises naturally from some physical model. And for this model, a non-gradient problem is still open. And also this type, there are still many open problems. So actually, so what is open problems? The decomposition of closed forms are not fully understood when first the interaction is not nearest neighbor case. So all in existing works, usually it's said that it's easy to extend the result to not nearest neighbor case, but actually there's some subtlety on the boundary condition, the limit of boundary term, so on. So, and there's no explicit result for this case, but I think this is not so crucial. But there are also very few results on the case with conserved quantities case. So that case also, so we need some condition between the relation of conserved quantities or something is still open. And so universal expression of diffusion matrix is also not clearly given. And also the case, the reversible measure is not product case, it's very hard, and there's only one result for the exclusion process with a mixing condition, nice mixing condition. And also the rate function is not uniformly positive, and bounded case is almost open and very hard. And the discrete case with this non-compact state space case is also not proved. And of course, as I said, the operator is an integral operator case, as I showed. That case is completely open. And once if we generalize the underlying space to some crystal lattice, such as triangular lattice or hexagonal lattice, almost generate some nice space, and this is also open. So there are many questions for this decomposition of closed forms. And of course, some case non-gradient models are solved without using decomposition of closed forms, but using some special property or specific property of that model. But we want to avoid this approach, so we really focus on this decomposition of closed forms problem. And a bit more precisely, what is the difficulty? So it's maybe many of you heard that spectral gap estimate of the generator is the most difficult part for this non-gradient method. But even we have this spectral gap estimate, still we sometimes have problem to prove the decomposition theorem, because we also need some other results like called moving particles lemma, which allows us to compare the Dirichlet form of mean field type with the local interaction type. And also we need to control some boundary derivative term, so which I cannot explain now, but this part is also non-trivial and not routine, and we often have some new problems. And the last point is a characterization of this harmonic form. This specific form appears always universally, but there's no abstract way to say that this term should appear, and there are no other harmonic form. So we always check this term appears by some limiting procedure. There's some from the boundary term, and we check some specific equation for each model. And proves that the solution of this equation is really characterized as this form. So there's no universal approach for this term, harmonic form. And for this difficulty, we try to work on this problem by separating the problem into geometric part and analytic part. So, for example, the underlying graph structure ZD and its nearest neighbor edges, or the one-side space, or this operator nabla is somehow geometric data of this model, which is kind of differential structure of manifold. On the other hand, new row or jump rate or invariant measures analytic data, and like a Riemannian structure. So we try to distinguish these two data, and we entangle the difficulties by an abstract and unified approach. Okay, thank you very much. I stop here.
Okay, thank you very much, Makiko. Let me allow everyone to. Okay, everyone's allowed to unmute themselves now. If you want to join me in a round of applause.
Thank you.
Let me make sure. Oh wait, no, now everyone's allowed. Okay, so anybody who has questions, just feel free to ask them. You can unmute yourself and ask a question. And maybe I'll start with one question. Maybe it was on the previous slide.
Yeah. Okay.
Okay, yeah, open problem.
Yep.
So,
yes.
So you said the reversible measure is not product, makes it very difficult. So you said there's one example. So what is the example of the result for non-product? Is this for open ASAP or?
No, exclusion process. Open ASAP. No. So it's reversible model, and with respect to Gibbs measure, finite range Gibbs measure of exclusion. So the jump rate R is okay. So it's Rxy is not same with Ryx, but still a reversible case. So it exists. So it's not Bernoulli product, but so Gibbs measure, and so can you imagine the case? But at least if we start from some finite range Gibbs measure or exclusion state space, somehow we can construct a reversible jump rate from this measure. So
okay.
Yeah.
Because I think
kind
also
of,
for the open ASAP with boundary conditions, you typically don't get product measure, and I think there are some results that have been proved about the hydrodynamic limit. It's not at all complete to my knowledge, but
okay, so somehow, as I said, hydrodynamic limit itself is proved using some different techniques. So means we can avoid to use decomposition of closed form, but and especially ASAP case, asymmetric case, we don't need this decomposition of closed form because it's Euler scaling. It's not diffusive scaling. So, but yeah, my question is actually when this model is diffusive scaling and we want to understand the model somehow abstract way, means if we want to, we don't want to use some specific property of the model, then we should prove decomposition of closed form somehow. And so decomposition of closed form itself is, I think, interesting question. And this part is not proved for not product case, not product measures, and only just one result exists, I think.
okay, thank you.
So Makiko, can I ask you?
Yes.
Yeah, so, well, thank you for your talk. It was a very nice talk. And so, what is something that always puzzles me is that why this decomposition? I mean, why this there has to be exactly the I mean, why this is in this decomposition of closed forms there appears exactly the extra terms in the composition and not less, not more.
Yes,
So
yes. Thank you very much for the nice question, because this is our problem for this abstract approach and geometric approach. And so next talk, Kenichi will explain why. So it's very nice point. And from the known strategy or from the known proof, we don't see why there's the form, the harmonic forms. And if we have multiple conserved quantities, let's say C, then we should have D times C number of forms, but it's really mysterious. But now we understand, so after 1 hour, maybe you will see why.
okay. That's good then.
Okay, well, so maybe we should transition now to the second talk. So let's all again thank Makiko. Okay, and I'll pass this off to Milton, who will chair the second talk.
So,
Very good. So Kenichi, can you share your screen now?
okay, I will do this. Is it working? Is it working?
Yeah, it's working. Very good.
And can you hear me?
Yes. Okay. So now the second talk of today is going to be a continuation of what Makiko was saying. It's going to be given by Kenichi Bannai from Keio University. It's going to be called a geometric perspective from the theory of hydrodynamic limits. So thank you very much, Kenichi, for accepting our invitation. And now you have a time.
Yeah, thank you very much. Yeah, I really appreciate allowing me to give a talk at the seminar with Makiko. Yeah, as Makiko said, I'm not a probability theorist. I'm a number theorist in arithmetic geometry. So I usually do number theoretical, algebraic, geometric things, and analysis is not my thing. But surprisingly, the skills that I have, it was Makiko's observation that we could use to attack problems concerning hydrodynamic limits, and that is what I want to talk about. So the plan, so in Makiko's talk, she talked about what is hydrodynamic limits, and she explained the strategy of proof of hydrodynamic limits, that there are very strategy for proving them, and that the decomposition of closed forms is essential for non-gradient models in both strategies. And as she explained, to prove the decomposition of closed form, it requires a very tough argument dependent on models, so it's not routine at all, as far as I understand. I'm sorry, yeah. And so why the difficulties, what Makiko just explained, is there are lots and lots of factors, but the first three things that she talked about, it depends on the measure or the stochastic data or things like this. And the last part, last part about the harmonic form that you just asked about, yeah, this seems to be independent of measure. And so I think it was a very keen observation of Makiko is that this harmonic form part, since it is independent of measure, there should be some method independent of measure theoretic stochastic method to handle this part. And that is what we want to talk about. So the top three concerns the stochastic part, and the bottom one concerns the geometric part. And with analogy with Riemannian manifolds,
Kenichi,
stochastic, yes?
Sorry, so it seems that your slides are frozen in the first slide. Are you?
I see. Ooh. How
And there's also
it not?
some sort of box to the right.
Mhm.
Maybe that's related.
Maybe I try sharing again. Okay. I'm sorry. Share. Mhm. Which slide do you see?
Why not routine?
Why not routine? Okay.
Okay, so
Okay.
Kenichi, if
Mhm.
you
Mhm.
if you change
Mhm.
the window on your computer, the sharing ability
Stops.
gets frozen, gets stuck. So
I see. I see. So I just push right. So this is okay.
Okay.
Okay. Okay. Yeah. So the first three things are dependent on measure, and the last harmonic form part is independent of measure. And so the first three parts is very stochastic data, and Riemann analogy with the Riemann geometry, it's Riemannian data, whereas the last part about harmonic forms, it's geometric topological data. And so what we wanted to understand was this last part, trying to understand this theory without the stochastic data, what we can say. And the critical observation was that we can characterize the harmonic form by a cohomology of the underlying geometric data of the models. So you asked, why is it d-dimensional? So we can really use cohomology to say what it is, and that it really is d-dimensional for a local version, not exactly in this case, but in a very similar case. And so what do we mean by the geometric analog or the local analog?
Okay,
The theorem.
I think the screen is still not updating. Have you moved from that difficulties slide?
Yes, I moved.
Okay, yeah, it hasn't updated. There's maybe if you don't use it in full screen, that might.
Okay.
Why don't you just do it in this form? This is fine.
Okay, can you see?
Yeah.
Yes.
Just do it in this form.
Okay. It's a little bit difficult because everything is on the screen now. So what would be okay? Okay, so yeah, okay. In any case, so yeah, okay. So the theorem that Makiko introduced, the decomposition theorem of closed form for exclusion processes, it was. Can you see my mouse, or is it okay?
Yes. We can see
Okay,
your mouse.
Okay, then. Yeah, so it's the theorem here. And so the decomposition is of this form. And our main theorem is not exactly a decomposition on this form, but a geometric version of this decomposition theorem. So it looks very similar. So suppose you have an omega, which is a local shift invariant local form, not a L2 form, but a local form. And if it's a shift invariant closed form, then we have a similar decomposition in this form. And if you compare the top and the bottom, it's very similar. The harmonic term is exactly the same. Harmonic form is exactly the same. The first part, in the L2 version, you have a limit. But in the local version, it's local, so you just have the local form. And what is the local form? Well, local form is dense in the L2 form, so it is very close. It's not exactly the same. It is very close, so one can say that our theorem is a local analog of Faradan's theorem. And so what is good about this theorem is the advantage of our theorem is that the proof is very abstract and it's applicable to a wide variety of models. So as Makiko explained, the decomposition theorem for the L2 version, you need really very hard techniques to prove it for each model. But our theorem works for a very general wide variety of models, not only models over the Euclidean lattice, but more general crystal lattices, and probably on Cayley graphs. And it's also valid for models with multiple conserved quantities, like the multicolor exclusion process. So one good thing about this theory is that the proof is very abstract. And another good thing is that it depends only on the geometric data of the underlying model. So the proof is purely algebraic combinatorial, and it's really independent of stochastic data. So the reason why this d-dimensional thing comes out is because this harmonic form depends only on the geometric data and not on the stochastic data. And we can also give interpretation of conserved quantities and harmonic forms by asserting cohomology of the underlying geometry of the model. So that are the advantages. And so the rough idea how to do this is we use cohomology theory. And if you don't know what cohomology theory, then it may sound very difficult, but it's just an algebraic method to extract important information from algebraic or geometric objects. And it's a very formal thing. And the rough idea which we use in our case, for example, in the cohomology of a torus is just the real plane divided by Z2. And so it's a quotient of R2 by the action by translation of Z2. And in such case, the cohomology of this quotient space, in our case, the torus, is just given by the group cohomology of the H0 of the universal covering space. So what I want you to understand is that the cohomology of a quotient space is calculated by the H0 of the universal covering space plus group cohomology. So if you want to understand some quotient space, then you just need to know what the cohomology of the universal covering space and the group action in between. And in Varadhan's decomposition theorem, there's a shift invariance coming out. And what this shift invariance corresponds to is the quotient space with respect to this action of shift. So in order to construct a good cohomology theory of the quotient, our idea, or Makiko's idea, was to construct a cohomology theory of the universal covering space. So a good cohomology theory on the infinite graphs. And we use this to calculate the cohomology of the quotient space. Okay. But that is all just rough ideas of what I wanted to explain. So I want to describe the plan of what we do. And first I will talk about what our abstract setting is, the model that we want to use. Then I will explain what uniformly local functions. So it's a version of local functions which is good on infinite graphs, and conservative quantities, how they relate. Then I'd like to explain what uniformly local cohomology is and the key theorem of our research. Then also the main theorem, the geometric version of decomposition of closed forms. That's what I would like to explain. So that is how I would like to go. Yeah. So I think it's better if I can do it full screen, but does it stop? Yeah, does it stop still?
Let's check.
Mm-hmm.
So try to go one.
Mm-hmm. Mm-hmm. Is it stopping?
So we see your plan.
Mm-hmm. So it doesn't move.
Yeah.
So having multiple desktop is not good, maybe. Is that the case?
Yeah, probably yes.
I see. How do I stop having multiple desktops? Oh, I see. Do you see model?
There's a box on the right side. I don't know if by by removing that gray box, you would help yourself, but
Gray box.
oh, maybe it's not showing up on your side.
No, it's not. Okay. I'm sorry. Yeah, sorry, it's not working.
Well, from our side, we can see perfectly if it's not full screen. So
okay, yeah. So everything comes out on the screen at once, so it may be a little difficult to see. So that's what I was a little bit worried about. Yeah, yeah. So I'll just go with the abstract setting. So the model. So Makiko first introduced the this model, the state space of exclusion processes on the torus in D equals 1. So first, for the model, there was the underlying graph of the dynamics, which in this case was a torus. Then there was the permitted states at each vertex, which was 1 or 0, corresponding to if there was a particle or not. And so we want to abstractize this. So we need some space where the dynamic takes place. Then we have some set which describes what is permitted at what states are permitted at each vertex. And then there was also this rule of how things move, interact on each edge of the underlying graph. And so we extract this information, we call it an interaction. So it is a map from S cross X to X cross S. So in our case, so if it's 0 and 1, and if you take this edge, and if you interact it, then you just exchange the 0 and 1 and get 1 and 0. So the rule, the interaction in this case, describing this model, the exclusion process is just interchanging S1 and S2. So like this. And so, yeah, so these are the information that we want to get the geometric data of the model. So the geometric data of our large interacting system, so X is a locale. So we call, so these three information is the geometric data to construct our model. The graph where the dynamic takes place, we call a locale. The set of states, S, is a set, is where the possible states on each vertex, and phi interaction is the interaction between states on adjacent features. So if you have these information, then you can construct the geometric data. And more mathematically, the type of graph we take is a connected, locally finite, simple, symmetric directed graph. The set of states, we just take some non-empty set with a fixed element, which we call a base state. And the interaction, it's a map from S cross S to S cross S, satisfying a certain condition that I will explain later. And using these three data, we can construct the configuration space of our object. So, and it's a geometric object containing important information of the stochastic process. And the examples of the exclusion process, so the graph was the torus, the set of state was 0 or 1, and the interaction was just exchanging the two components. And the configuration space is what Makiko called the state space, just this space. And there is a structure on this configuration state describing what kind of transitions are allowed in this process. So Sx and phi, the configuration space makes a graph. And because you have a graph, then you can consider the cohomology of this object. Okay, and so, yeah, I think because I cannot show you a little bit detail, so just some examples, and I think I'll skip by some. So the example of set of states is 0 or 1, for example, is one example, and 0 or 1 can have many meanings, like no particle and 1 particle. Or another example is 0, 1, 2, no particle, 1 particle, or 2 is another type of particle. So in the case of multi-color exclusion process, 0, 1, 2 means like this, 2 means a red particle, a different particle. Whereas in a general exclusion process, 0, 1, 2 could mean 0 is no particle, 1 means 1 particle, or 2 is 2 particle. So yeah, if you have a set of states, then you can give it many meanings, or like amount of energy and things like this. And not just 0, 1, 2, you could go from 0 to kappa, and then you can have more types of particles or more number of particles at that point, or more energy at that point. I mean, to abstractly define various types of models, you can use S to interpret it in many ways. So the set of state is something like this. Next, I want to talk about interactions. So interactions are, those give interaction between states on adjacent vertices. So in the case of exclusion process, you just exchange the two components. So this guy goes to here and this guy goes to here, like for say, yeah. And for the multicolor exclusion process, you can also, it's just reversing the two. So yeah, this guy goes here and this guy goes like this, yeah. So something like this. And yeah, there's also a multicolor exclusion version process. So yeah, you can use this to describe many different types of interactions. In the case of general exclusion process, so if you have two particles, then one particle goes like this, or one particle goes like this, and one particle goes like this, and this. And so, yeah, so this interaction, if you have an interaction, you can describe the movements of these particles. And the one condition that we impose on the interaction is that if you do an interaction like this, and then reverse the direction of the arrows, and then do the interaction again, then you are where you started. So that's the type of things, that's the type of condition that we impose. So this formula here, which it just says that you interact, reverse the direction of arrows, interact, then reverse the direction of the arrows, then you are back to where you started. So that is how, yeah, that is what interactions are. So yeah, that's what we define an interaction to be. So it's a map from S cross S to S cross S satisfying the property that I just described. And the last information. Yes.
So maybe there could be more than one type of interaction, no?
Yeah, there could be many types of interaction, and for each, you choose an interaction for each model that you want to describe. Or
I mean, because what I mean is that I don't know if you in your definitions you include the following type of situation. You have, let's say, two type of particles, and you can have k at most k particles at each side. So when you do these drawings, you have you have two. I mean, two things can happen, no? Because you can pass a blue particle to the other side, or maybe a red particle to the other side.
Right now, for our situation, so for each edge of the graph, there is a unique interaction or unique thing that happens.
Okay.
So depending on the original situation, something unique happens. So
okay.
Yeah, that's what we define. Yes.
Okay.
For now, yeah. The current model we have is like this. Yes. And the last set of data is the locale, is where the dynamic takes place. And so I think generally, in many cases, it's usually the Euclidean lattice. And as far as I understand, hydrodynamic limit for the non-gradient case, it has been proved exclusively for Euclidean lattices. But for our locale, we take a graph where we take the graph to be some connected, locally finite, simple symmetric directed graph. So yeah, so connected, locally finite, simple, symmetric, directed graph. And when I say directed graph, I mean that, so the edges is a subset of X cross X. So there are no multiple edges. And so example of locales is like for the torus that Makiko used is an example. Euclidean lattice is another example. And if you just look at the Euclidean lattice, then maybe you only think that there's only the nearest neighbor. But if you consider the locale with two nearest neighbors, then you can model something where there's an interaction with two nearest neighbors. Also, crystal lattices like the triangular lattice and hexagonal lattice, those are examples of locales. And also the Cayley graph. So for some finitely generated group, and S being the finite set generating G, then you can also construct a graph which satisfies the property of locale. And so these are the data that we use to construct our geometric data. And so, yeah, if it's not symmetric, for example, this graph is not symmetric, so this is not a locale, but if you add all the edges going the other way, then this becomes a locale. So when I draw a diagram like this, I usually implicitly mean that all the reverse arrows are also in the graph, okay? And so, yeah. So the model, the geometric data that we need to define our model is this. So we can deal with models that fit in this framework. So like the exclusion process and the multicolor exclusion process and generalized exclusion process and lattice with gas, and many models fit in this framework. And so, okay. So next, I want to describe what the configuration space, which is our object of interest, is. And so the configuration space is just the product of the local states on all the points of X. So if X is a finite locale given by this, and S is 0, 1, then all the possible configurations are like this. So each node or each vertex is either 0 or 1. There's a particle or there's no particle. So the configuration space is like this. And to this configuration space, right now it is just a set, but we want to add some transition structure describing all the possible transitions. So if you have a configuration like this with 2 points here, and if you choose this edge, then the exclusion process is just interchanging the points on the edges. So this comes over here. So that would be how, so this and this is connected by the action induced from the edge on E2. So by using this transitions, all the set states have relations. So this is related to this by E2, and then all the other configurations are related by these things. So in a sense, you get a graph describing what are the possible transitions which are allowed on the states. And if there were 16 elements for this example, and so these 16 elements are configured into a graph like this. And so you have 5 connected components in these cases. So that is what is a configuration space with transition structure. So yeah, so it's not just a configuration space, but you have a structure of a graph coming from the interactions, which we call transition. And so this is a geometric object, so we can define cohomology for these things. But before we go into the cohomology, I want to describe what uniformly local functions are. These are a generalization of local functions, which will be used to define our cohomology theory. So this is a good class of functions on the configuration space of infinite graphs, which gives a very nice cohomology theory. And so first, what are local functions? This is what Makiko was using. So it is a function on the configuration space, and there exists a finite number of vertices, and this function depends only on the finite number of vertices. So a local function is something like this, and we denote the set of local functions by a loc, like Makiko did. And actually, this local functions, it is a subset of functions on S, the configuration space, but it is also a subset of the maps on the configuration space star. The star means configuration which is at base state for all but finite vertices. So we fix the base point on each state. So we use this S star X a lot. And for local functions, we define the diameter to be the diameter of minimum lambda satisfying this local condition. So a local function, you have some finite lambda, which the function depends on, and you take one with a minimum diameter to define the diameter of the local function. And then we define a uniformly local function to be some function on Sx star, which is expressed as possibly infinite sum of local functions whose diameter is uniformly bounded. So this is what uniformly local is. It's a generalization of local functions, meaning that you could have possibly infinite sum of local functions, but with some condition on diameter, so the diameter does not grow too rapidly. And then we call C unif the uniformly local functions. So a local function is contained in uniformly local functions, which is contained in the maps of Sx star to R. So first, these are uniformly local functions. And the very nice example, or the most important example of uniformly local function is given by the conserved quantities. So we define a conserved quantity to be, so we define it very algebraically. So we have that set of states and we have the interaction. So we define a conserved quantity to be a function on the set of states whose sum is preserved by the interaction. So we first define conserved quantities very, very locally, just a function on states on a single vertices, such that if you interact, then the sum is preserved. So this gives a very algebraic construction or algebraic characterization of conserved quantities. And example is, for example, number of particles or amount of energy or things like this, that which you would imagine to be conserved in many cases are conserved quantities. But but this linearity is something that we impose. And if we impose this condition, then you can see that it is preserved by addition and scalar multiplication. So the set of all conserved quantities becomes an R linear space. And actually this R linear space we feel is a very important invariant of the interaction. Because if you define an interaction between S cross S and S cross S, then you can define the set of all conserved quantities conserved by this interaction. And this dimension of this vector space gives you the number of independent conserved quantities. So we think this is a very nice way to characterize conserved quantities. And I just explained somehow that in each of the cases, there is a nice conserved quantity. For the generalized exclusion process, the number of particles is, for example, a conserved quantity. And in the case of multicolor exclusion process, if it's 0, 1, 2 with 2 colors, then there are 2 linearly independent conserved quantities, one for each color, the number of particles of each color. I mean, if you have kappa particles and multicolor, then you have conserved quantities for each of the color of the particles. So so this is an example where it's multi-conserved. So this notion of conserved quantity fits with the notion of conserved quantities that is already used. And then this conserved quantity actually gives a uniformly local function as follows. So Gz, the conserved quantity, was a function on S. But if you sum over all the point on X, then actually this is an infinite sum. But if you restrict to, I'm sorry, this should be Sx star. If you restrict to states, configurations, which is at base state at all but finite number of points, then since conserved quantity is 0 for base state, so this becomes a finite sum. So what is very nice about this working on Sx star is that you can define a function really on Sx star, which looks like an infinite sum, but is well defined. So this conserved quantity gives uniformly local functions. And yeah, in the case of multicolor exclusion process, this uniformly local function corresponds to the conserved quantities. It gives you what you think it would give you, the total number of each color. So the first conserved color quantities for blue, so it gives you the number of blue dots. And the second one is the red, so it gives you the number of red ones. So it works very well. And concerning conserved quantities, so we're trying to construct an abstract theory for our proof to work. So we need some more conditions on conserved quantities to make the theory work. And one important criteria or one important assumption needed for our theory is what we call faithfully quantified. So this will be one assumption we will impose on our main theorem. We assume that the interaction is faithfully quantified. And what this means is that the space of conserved quantity becomes finite dimensional. And for any locale x and configurations S and S prime and Sx star, if all of the conserved quantities coincide, then there's a finite path from the state. So if you have states with exactly the same conserved quantities for any conserved quantity, then you always have a path going from one to the other. So that is the assumption faithfully quantified. And this faithfully quantified condition is equivalent to the stochastic process with fixed conserved quantity is irreducible as a stochastic process. So it means if you fix all the conserved quantities, then the set of states becomes connected. So that, I think that is what irreducible is. So this is how it is related. Yeah, and so yeah, I wanted to give examples, but yeah, so if you have a locale with 3 points and the multicolor exclusion process, then all the possible states are here. There are 27 possible states. And the conserved quantities, the first conserved quantities is here, second conserved quantities here. And if they coincide, they are in the same connected components. So if you fix the conserved quantities, then all the states are in the same connected components. Yeah, so this is the one with this. And yes, and so in this case, there are 10 connected components corresponding to each of the possible conserved quantities. And yeah, so you can use this conserved quantity to see how much connected components Sx star has. It is bijective with the image. If you take the basis of the space of conserved quantities and embed it into RC phi, then the points of this image corresponds to each of the connected components. So you can use this to look at how much connected components your configuration space has. Yeah. And so that I just explained what uniformly local functions were, what conserved quantities were, and how you can use conserved quantities to look at the space. So faithfully quantified is a very important condition that we assume, which makes the theory very nice. And so we use this uniformly local functions to construct a cohomology theory. And so I want to tell you what uniformly local cohomology is. So I don't know how much homology people know, but just very roughly, homology is a systematic method to derive invariance from geometric objects. And the zeroth homology gives the connected components of a topological space. H1 gives the number of class of closed path. So in case of like a torus, H0 is you have rank 1, so there's one connected component. And H1, you have two, rank 2, which correspond to each of the direction of the torus. And the explicit definition is like this. And if you haven't seen this, then it may look very complicated, but it's just an algebraic method associating invariance to geometric objects. So if you have a diagram like this, then there's one connected component and no closed cycles. So H0 is rank 1 and H1 is 0. And if you have a diagram like this, then you have one connected component and one closed cycle. So you have rank 1 for H0 and rank 1 for H1. So this is a very algebraic method to extract very important topological invariants. And so the example that I showed you with 5 connected components, if you look at the homology, then because there are 5 connected components, there are 5 rank 5 homology for H0. And because there are 5 closed paths, H1 has 5 rank 5 closed path. So that is how you use cohomology to extract information from geometric objects. But there is some problem is that we want to deal with infinite graphs. And if you have infinite graphs, then the configuration space on infinite graph is generally not countable, not locally finite, and it's not even connected. So generally, both H0 and H1 becomes infinite dimensional. And so that's not too good because infinite is a very large number. And so we want the suitable theory where H0 becomes finite dimensional. And we also want H1 not to appear because we do not want to see closed path, because in our stochastic process, we don't want to remember how the process transferred or how it evolved. We just want everything to rely on just the current state now. So we would like a theory where H0 is finite dimensional and H1 disappears. And that is where we use uniform local functions and cohomology. And a little bit about cohomology. What is the difference between homology and cohomology? Well, homology, you look at the space itself. The cohomology, you look at the functions on the space. So you just take the dual of the complexes defining homology, and then you use the functions on these spaces to construct the cohomology. And so you have some differential here. And you don't have to follow everything, but what I would like to stress is that there is a very natural differential coming from the general theory of cohomology. And this differential coincides with the differential that is used in the hydrodynamic limit, or the differential that Makiko used in describing hydrodynamic limits, this delta F or nabla EF. These are very natural differentials coming from the geometric structure of the configuration space with transition structure. And then cohomology is just defined using this complex. And however, this cohomology is just the dual to homology. So this infinite dimensional problem does not disappear. So we have to do a little bit more. But what is good about cohomology is, so homology, you look at the space itself, so it's very hard. It's less versatile. But cohomology, you're looking at the functions. So you can change the functions to change what you're looking at. For example, a torus, you can look at it as a continuous, as a topological space, or C infinity manifold, or in many cases, complex manifold. So a complex torus has many structures. And to extract information concerning each structure, you can use various functions like the continuous functions, or C infinity functions, or holomorphic functions. So a choice of functions gives theory corresponding to each structure that you want to look at. And so in our case, we had a good class of function called uniformly local functions. Actually, we see later that it is very good, but we have this nice class of functions. So we use this uniformly local functions to alter the natural things coming from general theory of cohomology. We change from maps to uniformly local functions, and maps on the forms to uniformly local closed forms. And then we can use this to define uniformly local cohomology, just imitating the case of the usual cohomology. So that is how we define uniformly local cohomology. And Makiko said that I should explain what closed forms were. So yeah, I should explain a little bit. So forms are maps on transitions. And then you can define integration of forms with respect to path, because path is a system of transitions. So path is just so the edges on the configuration space. And so forms is a function on the edges. So you can define the integration just by taking the sum of the values at all the edges in the path. And a form is closed if the integration is 0 on all closed paths, which means the integration is independent of the path chosen. I mean, you want this because you want things to be independent of the choice of path going from point A to point B. And you don't want to remember everything of how you moved from point A to point B. You just want to know you just want the information of where you are. So that is why closed is an important condition that we impose on our cohomology. And so that is uniformly local cohomology and closed forms. One more condition that we impose on the locale itself, the underlying graph itself, is a condition we call transferability. So yeah, it's a little bit strange, but useful condition is that a locale X is weakly transferable if for any ball, if you remove the ball, then the remaining complement is a finite disjoint union of connected infinite graphs. And it's strongly transferable if you remove any ball, then the complement is really a connected infinite graph. So if you have a Euclidean lattice for D greater than 1, then it's strongly transferable, because if you remove a ball, it's always connected. And if it's Z1, then it's not strongly transferable, because if you remove a ball, then it splits into 2 parts, but it's still weakly transferable. And there's a condition in between called transferable, but I won't go into details about this. But so this is the condition we impose on the locale. And another condition that we may impose on the interaction is that simple. We said that we could deal with multi-conserved quantity models with multi-conserved quantities, but the systems with just one conserved quantity is much simpler. So in that case, we say that it's simple, and then you can prove stronger results. So for our main results, the conditions we impose is that so phi is always faithfully quantified, meaning that the stochastic process is always irreducible if you fix all the conserved quantities. If X is transferable, then we can prove our key and main theorems. If the locale is only weakly transferable, then right now we have to assume that the interaction is simple to get our main results. But this is the results we use to prove our main theorem. And before going to our main theorem, I want to explain what our key theorem is. This is the calculation of uniform local cohomology. If we assume all the conditions that I just mentioned, then we can prove that uniform local cohomology, you only have the 0th cohomology, and the cohomology greater than 1 disappears. And if it's faithfully quantified, then this conserved quantity is finite dimensional. So you really have a good cohomology theory, which is finite dimensional, and then you only have H0 coming out. So this allows you to look at the configuration space as a certain universal covering space, in a sense, because you don't have higher cohomology coming out. And then we use this to prove we use this key theorem to prove our decomposition result. And so our main result, the geometric version of the decomposition of closed forms. So the idea, so our main theorem, in the case of exclusion process on ZD, it's the geometric version of the decomposition theorem. So I explained at the introduction it was of this form. If you have a local shift invariant closed form, then you can split it up into these two parts. The first part is sum over all the translations. The second part, you have this harmonic form for any local function like this. And well, so what is translation? So if you have an element in ZD, then using this element, you can translate this like this, So if you look at ZD as a group, then it gives an action of the group ZD onto the locale ZD. So we want to separate the group from the locale. In the classical case, it's all both ZD. So, I mean, there's maybe no point in separating, but in case of crystalline lattices, the group is not necessarily coincide with the locale. So the separation is something very important. And so what is this shift invariance? Shift invariance means, if you look at it in terms of group action, it means invariant under the action of the group. So the K local, the shift invariant closed forms that Makiko defined, in our language, it is just the G invariant part of the uniformly local closed forms. So uniformly local is an infinite sum of local forms in some sense. So actually the G invariant part corresponds to shift invariant closed forms. And so, yeah, so the K local is given as this in our language. And this part here, you have a sum of F with respect to translation. So it's an infinite sum, and it's the sum over translation. So obviously it's invariant under the action of G. So this part in our language fits into here. So it's the uniform local functions G invariant. And then if you take the differential, then you have the differential here. So this part here in our language corresponds to this part here. And so if we understand this to prove this theorem, it becomes very, very formal. So our main theorem is as follows. We assume all the conditions that we assumed for our key theorem. And in addition, we assume that X has a free action of a group G, and that the abelian quotient G abelian is a finite rank D. Then we have an isomorphism like this. K log divided by E log is the d-dimensional sum of conserved quantities. Yeah, you asked why is it d-dimensional, or how do we know it's d-dimensional? Our main theorem, the proof for our main theorem, it follows from the key lemma I will explain shortly, but this really shows you that this is not the L2 version, but this is a local version. But this version, you can really prove that the difference is given by these d-dimensional things. So if you have many conserved quantities, if you have C conserved quantities, then this is C d-dimensional. So you can see this. And if you choose a choice of a fundamental domain of the action of G on X, then this is not only a quotient, it gives a decomposition. And actually, this decomposition coincides with that harmonic function, harmonic form. So if you have a conserved quantity, and if you look at the associated form in K log, it gives you really the harmonic form, which appeared in Makiko's talk. So that strange form really has a very nice meaning in terms of cohomology. And I think that was Makiko's very keen observation that started this research in the first place. And so a little bit about the main theorem. So ours is the geometric local function version. So it's not really the L2 version, though these things are subsets of this, and we are hoping that maybe these are dense in here. But so our decomposition gives a certain topological decomposition. Also, if you consider metric, there's an orthogonal decomposition coming from differential geometric data coming from the inner product. And so as Makiko explained, the diffusion matrix giving the hydrodynamic limit equation comes from the comparison of these two decomposition. And so this looks very much like the decomposition in Hodge theory, where you have a topological decomposition and a differential geometric decomposition. So I think this is very interesting in its analogy with differential geometry. And a little bit about the proof of our theorem. Actually, it's very fast if you know the formalism. Our theorem stated that the cohomology of H0 was conserved quantities and H1 disappears, which meant that this sequence is exact. So that was our key theorem. If you just take the G invariant part, then it gives you a long exact sequence associated to this short exact sequence, which is just linear algebra. And then so it gives you from the quotient to H1Z conservative, which you can show that it is isomorphic to the sums of conserved quantities. And then there's a standard way to construct an inverse in the other direction, which shows that this injection becomes an isomorphism. And this explicit construction in the case of the classical case gives the harmonic form that we wanted. So this proof is very fast using standard formalism once you have uniform local cohomology. So that is the proof of the theorem. And I think that is all I wanted to say. So we are working on ongoing and future works, and I just leave the slide like this. So thank you very much for your attention.
Thank you. And so now you can unmute yourself and clap your hands to thank Kenichi for his nice talk. So also, if you have some questions, you can just ask, unmute yourself and ask. So I do have some questions, Kenichi. So the first thing is that okay, so now we are you understand where this D terms comes in the non-gradient method, because it's just as you were saying, it's just a topological fact, no? This is just come from this geometric fact, so at some point somebody point me out this connection that this hydrodynamic limit should have something to do with Hodge theory. So I went to see what was this Hodge theory about, and discovered that even though it's a very geometric algebraic theorem, there is one key step on which you cannot get rid of analysis, no?
In classical Hodge theory, yeah, right. You need harmonic analysis, I think, yes.
So at some point you need to use some sort of Poincare inequality to prove that some objects are regular, no? That's and this is like the analogous of this spectral gap. So is that the case? I mean, is that you will always need a spectral gap or something like that to let's say to close the proof of hydrodynamic limits, or there is another way to do it? Because it seems that even at the level of the Hodge theory, you cannot get rid of this spectral gap.
Right. So yeah, I'm not a probability theorist, so maybe Makiko should answer, but from what I understand, so is spectral gap really necessary for hydrodynamic limits? It's an open question. And right now our method, I mean, we cannot prove the L2 case using our method currently as it stands. And yeah, we believe that we have to do some analysis like spectral gaps and boundary things. We currently think that, yeah, we have to do some analysis to understand these things, but yes. But yeah, but by sort of organizing everything, I think we have a better understanding of what and where the problems are. Yeah. Is this right, Makiko?
Yes. Yeah. So I really want to understand, do we need spectral gap or not? So this is, yeah.
So maybe for you, Makiko, I have a more technical question.
Yeah. Okay.
So maybe you still need spectral gap, but you can rid of the moving particle lemma.
Why? You think so?
Because somehow so the moving particle lemma is I mean, if you want to prove hydrodynamic limits, you don't only need the spectral gap inequality, you also need the moving you need the moving particle lemma proof of the spectral gap inequality.
Not only there, I think, because to control the boundary term, we always use some averaging with respect to some bigger box, like a 3n box, and there we need a Dirichlet form for mean field type. So boundary and some point in this bigger box, and we average over. And because of this averaging, we have a nice factor, 1 over n 1 over square, but we get instead a Dirichlet form for mean field type. So we control this boundary term by L2 norm and also the Dirichlet form of mean field type. So we need to control this mean field type Dirichlet form by something. Yeah, and so one way is using moving particle lemma. We control this Dirichlet form for mean field type by local one, and so local one is already controlled. So so maybe this part is not so well focused or discussed before, and we often focus on spectral gap estimate, but it seems this part is also some difficult part and not straightforward for new models like integral type or other differential type, but with some degenerate jump rate, degenerate rate function. Yeah, so still.
Yeah, but I mean, it's still very nice because now it's more clear. At least you already clear a big. You'll be able to clear up a bit part of the proofs of this hydrodynamic limits, no?
Yeah, I believe so. Yeah, actually, so once we can prove that this boundary term converges to some local function, then we have done, because we have this theory. So it's at least the one step is somehow getting rid of it's now become routine somehow. So we do not need to characterize this the limit of boundary term, and just we need to prove that boundary term converges to some local function. Then automatically this is local closed form, because this is a difference of closed form, two closed forms. So we know what is this. So yeah, I feel so now we can do some abstract theory for this L2 case even, but of course we assume spectral gap estimate or moving particle lemma, but once we assume this, we have some abstract theory, and actually we are not now working on this, and so the last part of which is more specific for each model is now solved abstract way. Yeah, I think so.
Okay, so I don't know if there are more questions. So in case there are no more questions, let's thank again Kenichi and also Makiko for this very nice couple of talks. Okay, so so you should be able to unmute yourself if you want to clap your hands. So thank you very much.
Thank you very much.
Thank you very much.
Okay, so well, and for the ones that are still here, so we'll see you next week as usual in the same at the same time for another couple of seminars.